Hello, my name is Florencia Leonardi and I'm an associate professor at the Institute of Mathematics and Statistics of the University of Sao Paulo. This is the first lesson of the course Statistical Model Selection for Stochastic Systems with applications to Bioinformatics, Linguistics and Neurobiology. In this first lesson, we will talk about the notion of irreducible trees, the definition of context tree of a stationary ergodic process, some notions about inference for the model parameters, and concentration inequalities for the estimators of the model parameters. So let's begin by introducing the notion of irreducible trees. So let A be a finite alphabet and let W, M, N denote the strings of symbols in A given by Wm until Wn. We are going to use the notation L of W here for the length of the sequence. So the length of the sequence Wmn here is m minus n plus 1. So we say the sequence S indexed by the integers from j to k is a suffix of a sequence Wmn, and we denote this by this symbol here if the length of the sequence S is smaller or equal to the length of W and the last symbols on both sequences agree. That means that if we have here the sequence W and we have the sequence S here, then the length of S needs to be smaller or equal to the length of W, and all the symbols in S, for example A, B, C, and D here, need to agree with the corresponding symbols in W, C, and D, okay? In the case the length of S is smaller, strictly smaller than the length of W, then S is said to be a proper suffix of W, and in this case we use this notation, okay? We also use this notation suffix of W to denote the maximal proper suffix of W. So if we have a sequence W here, W1 until Wm, then suffix of W is simply the sequence from W2 until Wm. Okay? So let's introduce some extra notation. Here, A star will denote the set of all finite strings on the alphabet A. A infinity will denote the set of left infinite sequences W between minus infinity to n with symbols in A. So let's introduce the definition of a tree. We say that the subset tau, subset of the union of A star with A infinity, is a tree if it satisfies the suffix property. This property says that no W in tau is a proper suffix of another S in tau, okay? So a tree tau is called irreducible if no string belonging to tau can be replaced by a proper suffix without violating the suffix property. So we are going to see some examples now about these two notions. Let's consider these sets of strings here, tau1, tau2, tau3, and tau4. Let's begin with tau1. Here tau1 is composed by the sequences 0, 0, 0, 1, 0, 1, 1, 0, and 1. We see that tau1 is an irreducible tree because no sequence here is a suffix of another sequence. You can see this easily that no sequence in this set, tau1, is a suffix of another sequence, and moreover, no sequence here can be replaced by a suffix without violating the suffix property, because, for example, if we replace 0, 0 with only 0, this violates the suffix property because now 0 is a suffix of this and of this sequence here. So tau is an irreducible tree. We see that tau2 is a tree, but it is not an irreducible tree. So tau2 is not irreducible. So we see that it is a tree because it satisfies the suffix property. No sequence here is a suffix of another sequence, but we can, for example, substitute this sequence here. We can remove this symbol 1, replace it by 0, 0, and we do not violate the suffix property. So tau2 is not irreducible. Here, in the case of tau3, we see that it does not satisfy the suffix property because here 0, 0 is a suffix of 0, 0, 0. So tau3 is not a tree. Okay? And in the case of tau4, we have that this set is composed by the sequences given by a 1 concatenated with k0. So these are the sequence 1, 0, 0, 0s with k zeros here, with k greater or equal 0, plus a single infinite sequence of zeros. So it's easy to see that no sequence here is a suffix of any other sequence in this set, so tau4 is a tree, and it is also an irreducible tree because if we replace any of these sequences by a suffix, we violate the suffix property. So tau4 is also an irreducible tree. So we can see that any one of these sets, in particular the sets that are trees and that are irreducible trees, can be represented graphically by a tree with a root on top and the leaves on the bottom here. So we read the sequences in the set are read from left to right, and in the tree here they are read from bottom to top. So, for example, here we have the sequence 0, 0 is the first sequence, the sequence 0, 1, 0 here, the sequence 1, 1, 0, and 1. Here we have tau2, where one more time we have 1, 0, 0, 1, 0, and 1. Observe that tau2 is not an irreducible tree because we can simply remove this symbol 1 here and we obtain a tree. So we do not violate the suffix property. But in any case, even if it is not an irreducible tree, it can be represented graphically as a tree here, as here. And here we have tau4, where we represent only a portion of the tree because it is infinite, so it continues here. And we represent, as before, the sequences with a 1 and some number of 0 here, okay? And this represents the infinite, semi-infinite context. One thing that I think I didn't mention is that we use this symbol lambda here to denote the empty sequence. So the root in the tree represents a sequence with no symbols and is represented by this special symbol lambda. So let's define a partial order on the set of trees. We said that tau is smaller or equal tau prime if for every sequence v on tau prime, there exists a sequence W on tau such that W is a suffix of V. As usual, whenever tau is smaller or equal tau prime, but they are different, then we know this as with the strictly smaller symbol. So we write like this here. Now let's define what it is the height of the tree. So L of tau is the height of the tree and is defined as the maximum length of a sequence in the tree, okay? And another notion that we are going to need in the following lessons is the notion of tree tau truncated to a level k. This is given by this set here. So observe that in this tree truncated to level k, we put all the sequences that belong to tau and have length smaller or equal k, plus the suffixes of length k of sequences in tau that have length greater than k. So let's see in the examples here, we have that the height of tau 1 is 3, the height of tau 2 is also 3. Okay, so 1, 2, 3, we count each level in the tree without counting the root, and the height of tau 4 is infinite. Okay, so, and what is, for example, tau 4 truncated to level 2? So level 2 is here. So if we want to truncate the tree tau 4 to level 2, we put all the sequences with length smaller or equal to, that here we have 1 and 1, 0, and then we put the other sequences truncated at level 2. So the only one is 0, 0 here. So this is the tree tau 4 truncated to level 2. So with these examples, we finish the first section of our first lesson. So let's see the definition of context tree of a stationary ergodic process. So consider a process xi, a stationary and ergodic process with law or measure p, assuming values in the finite alphabet A. For any finite sequence A, we write this P of W as the probability, as the stationary probability of the sequence W in any time, because as we are assuming that the process is stationary, the time here does not matter. Now, if S is a finite sequence, is such that P of S is greater than 0, we write P of A given S as the transition probability of the symbol A given that the past sequence is S. In particular, if S is the empty sequence, then the conditional probability P of A given S is simply the stationary probability of the symbol A. The function P that goes from A times A star to the interval 0, 1 is called the kernel of the process. So let's define what is a context for a stationary ergodic process. This is definition 2.4 in the book. So we say that a finite sequence S in A star is a context if it satisfies these three conditions here. The first condition says that the probability of S is greater than 0 or S is the empty sequence, okay? The second condition says that for all A in the alphabet and all W in A star, so W is a finite sequence, such that S is a suffix of W, the conditional probability of A given W is equal to the conditional probability of A given S. So that means that if in our process, if we observe here, if we want to know the probability here of seeing a symbol A, given that we saw S here, and here is the sequence W, that is, so S is a suffix of W, so that means that S is sufficient to predict the next symbol in the sequence. So given W, all that we need to know is the symbols in the sequence S. Okay? And the condition 3 says that no proper suffix of S satisfies this condition 2. That means that S is the smallest sequence satisfying these conditions. So these points 1 to 3 are to define what a finite context is, but we also need the notion of infinite context. So an infinite context is a left infinite sequence, S from minus infinity to minus 1, such that its finite suffixes of any order here have positive probability, but none of them nor lambda are context for the process. So let's see some examples. Here we have example 2.5 in the book, where we have the process xi taking values in this binary alphabet as a Markov chain of order 3 with these transition probabilities, where A and B are arbitrary in this alphabet A. So if you do not know what a Markov chain is, we recommend to check this on any book on stochastic processes, but informally speaking, a Markov chain is a process where, in order to predict the next symbol here in your sequence, you need to know a fixed portion of the past. For example, here over there 3, you need to know x minus 1, x minus 2, and x minus 3. So if you know what happened here in this fixed part of the past, then you are able to predict the next symbol in the sequence. So in this table, we see the values of these transition probabilities. That means that if we saw the sequence 1, 1, 0, then we have a probability of 0.7 to see a symbol 0 here in the position of x0, or 0.3 of seeing a symbol 1. The same for the sequence 0, 1, 0. Then we have a probability of 0.3 of seeing a 0 and 0.7 of seeing a 1. And here, as we have a variable a that can assume the value of 0, 1, then we have the same probability of 0.5 of seeing a 0 or 0.5 of seeing a 1 for both sequences 0, 0, 0 or 1, 0, 0. Okay? And here, in this line, we have the same probability of 0.2 of seeing a 0, even for any sequence of the form 0, 0, 1, 0, 1, 1, 1, 0, 1, or 1, 1, 1. Okay? So we saw that the sequence is 1, 0, 0, 0, 1, 0, and 1, 1, 0 are all contexts for the process. So in this case, the context tree of this process is the tree represented by these sequences. So the context tree of this process is 1, 0, 0, 0, 1, 0, and 1, 1, 0. So this is 1, this is 0, 0, this is 0, 1, 0, and this is 1, 1, 0. Okay? And these are the minimal relevant past sequences that we need in order to predict the next symbol in the sequence. Now, the last example is example 2.6, where we have a stochastic process taking values in the binary alphabet A0 equal to 0, 1, and assume that for any k and any finite sequences v and w, we have that the probability of seeing a 1 given v concatenated with this sequence composed by a 1 and k zeros is equal to the probability of seeing a 1 given that we saw the sequence W concatenated with this sequence of 1 and all zeros. So here we see that the context of this process are the sequences of the form 1 concatenated with a finite sequence of zeros for every k greater or equal 0. So this set. And we also have another context that is the semi-infinite sequence with all zeros between minus infinity and minus 1. So these are the context of the process. Why the semi-infinite sequence of zeros is a context? Because if we assume that all these sequences have positive probability, all the finite sequences in the process have positive probability, then any one of the finite suffixes of this sequence here is a context, because we always need to see a 1 in order to predict the next symbol. So the tree of this process here is the tree that we saw before that have a 1 and an infinite branch of zeros here. And this is infinite, okay? So this is our last example in this section. Okay, now let's talk about inference or model parameters. So assume we observe a finite sample of symbols in A denoted by x1, xn, generated by a stochastic process with log p and context tree tau star. So let d be an integer smaller than n. Then for any w with length smaller or equal d and any symbol a, we define this counter here. This counter nn of wa counts the number of occurrences of the sequence w followed by the sequence a in the sample, but beginning at time d plus 1. So if we have here our sample from time 1 until time n, okay, so suppose here we have the symbols x1 until xn, and here we have the integer d, then we begin to count the occurrences of I here at time d plus 1, okay? So w can occur here, and w must be followed by a here, beginning at time d plus 1. And then we have a sliding window where now we are going to consider the following occurrence, and that's until we arrive to time n, okay? So we have a sliding window counting the occurrences of the sequence w followed by the symbol a. Then we also define nn of w as the sum for all a of the occurrences of nn of w followed by a. So this is not the same as counting the occurrences of w in the sequences. Why? Why? Because here we are counting the number of times w occurs followed by any symbol in the sequence. So it's not the same of counting the number of occurrences of w, but it's very similar, and both definitions could be different by at most 1, but we need this definition here of n of w. So given a tree tau with height of tau smaller or equal d, we can define the likelihood of the observed sample x1n for this tree tau and any set of transition probabilities q as this product here. So here we are doing the product over every sequence w in the tree and every possible symbol a in the alphabet of the transition probability q of a given w to the power of n of wa. That means that this transition probability occurs this number of times in the sequence. So this represents the conditional probability of the sample given the first d symbols. Okay, here we compute this likelihood with the convention that 0 to the power 0 is 1, okay? Because it can happen that some transition probability here is 0 and some counter is 0, but there is no problem on defining this likelihood with this convention here, okay? So here Q is any probability distribution over the alphabet A, okay? Now we defined these counters, we can define the maximum likelihood estimator of the transition probability of a symbol A given a sequence W as this ratio here. So we do the ratio of the number of times the sequence W occurs followed by the symbol A divided by the number of times the sequence W occurs followed by any symbol in the alphabet. So these are the maximum likelihood estimators for the transition probabilities. Okay, so this definition is valid when this counter here is greater than 0. Okay, if not, it's not defined. But it is not a problem because with n of w is 0, then the sequence WA cannot occur, and then we can define this empirical probability as any distribution on A in the case that n of w is 0, okay? So the maximum likelihood of the sequence x1n conditioned on the first d symbols for this tree tau is given by this expression here. So here we have replaced, if you remember, before we have here any probability distribution over A. So we have here Q of A given W, that was any transition probability. And in this definition, we substituted this Q of A given W by the maximum likelihood estimator. So this is the maximum value the likelihood can have for any transition probability. So let's end this lesson by seeing some concentration inequalities for these empirical probabilities. So we know that by the ergodicity of the chain and the ergodics theorem, these empirical probabilities go to the true transition probabilities of the process almost surely when n goes to infinity. Okay? For every fixed sequence W in the set of finite sequences and every symbol in the alphabet. But we need stronger results to prove the consistency of the context tree estimators that we will define in the following lessons. Why? Because this result here is only valid for a finite number of sequences, but in general, when we want to estimate a context tree, we need concentration inequalities for an unbounded subset of sequences. So these are the results we are going to see in a moment. In order to prove some of the concentration results we have in the book, we need some assumptions on the process. So the principal assumption is this assumption 2.7 that we see here. We say that the process xt satisfies the following loss of memory condition that states that this symbol alpha, that is the sum of these coefficients alpha k, is finite, where this alpha k is the supremum over all the symbols in A and all the infinite sequences U of the difference between the conditional probability of the symbol A given the sequence U, but having a gap of length k. So here we are saying that we have the probability of xk being equal to A here, given that from x minus infinity, let's represent this, until x0, we have a sequence U, okay? So this first probability here is the conditional probability of seeing this symbol here, given that the past with a gap here of length k, given this sequence, infinite sequence U in the past from minus infinity until 0. And this alpha k is bounded the difference of this probability from the stationary probability of seeing simply the symbol A without conditioning on any past, okay? So here we assume these coefficients alpha k decay to 0 sufficiently fast in order to this coefficient alpha here be finite, okay? So the first result we prove in the book is this concentration inequality for the counter Nn of WA, okay? So this is theorem 2.8 in the book. It says that assume the process xt satisfies assumption 2.7. For any finite sequence W with L of W smaller or equal D, any symbol A and any t greater than 0, the following inequality holds. So here we have the difference in absolute value between the counter, the number of occurrences of W followed by A, minus N minus D, so the length of the sequence where we are counting these occurrences, that is N minus D, times the stationary probability of seeing this sequence WA. So this statement says that the probability of this difference in absolute value being greater than t is smaller than this expression here, okay? Observe that we can take here a t of order square n minus d times log of n, and then the probability will be of order n a minus c over d plus 1. So this probability is going to 0 when n goes to infinity, okay? So we can apply theorem 2.8 to bound the difference of the empirical probabilities and the true transition probabilities, obtaining this corollary. So assume the process xt satisfies assumption 2.7. For any finite sequence W with P of W greater than 0 and L of W smaller or equal D, any symbol A in the alphabet A, any t greater than 0 and any n greater than d, the following inequality holds. So here we have the difference in absolute value of the empirical probability of A given W and the true probability of A given W. So the probability of this difference being greater than t is smaller than this expression here. In this expression, we have the size of the alphabet A here, the coefficient alpha obtained from assumption 2.7, and the maximal length of the sequence. Here, an upper bound on the length of the sequence that is d plus 1. Here also occurs the probability of the sequence W. Okay, so Observe now that as these numbers are between 0 and 1, we need some t going to 0 in order to this bound here makes sense. So we can take a value of t of order square root of log of n over n minus d, and then we have that the bound in the right hand side converges to 0. Then this probability converges to 0 when n goes to infinity, assuming that all the other constants appearing in this expression, like p of w, d, and alpha, are bounded from below or above, okay? Observe that as this bound here in the right hand side depends on the probability of w and the length of the sequence, then in order to control this probability for a set of sequences, we need to control the way in which this d grows or this p of w decreases with d and with n. And this is not good when we need to bound the probability of an unbounded set of sequences. But fortunately, we can show that in particular for sequences that are greater than context in the model, we can obtain upper bounds that does not depend on the parameters of the model, only on the alphabet size. So they are universal on the class of stationary and ergodic processes. So this is the statement of this theorem 2.10. It says that for any sequence W having a suffix in the context tree of the process with L of W smaller or equal D, any A in the alphabet and any T greater than 1, we have that the probability of this counter times this square distance here, this is the square variational distance basically. So the probability of this expression here being greater than t is smaller than this bound here. Observe that this bound only depends on the size of the alphabet. So it can be applied to any sequence W that is greater than a true context in the process. The proof of this result follows by observing that this difference here multiplied by nn of w is a martingale, and then we can use concentration results for martingales and some tricks to obtain this bound in the right hand side. Observe that in this case we can take a rate t of the order z log of n, and then we have that the right hand side goes to 0 when n goes to infinity. So this is the end of this first lesson, and I hope I meet you in the following lesson, where I'll talk about some applications to estimate the context tree, and I'll show you an application to the classification of proteins into families.